So I will present this flame project, which is financed by Manutech-SLEIGHT, and for which I work both on the Mine Saint-Étienne at the Laboratoire Friedel and in the Laboratoire at the university. So FLAME stands for Mechanical Consequences of Femtosecond Laser Irradiation of Metals. So I will introduce this subject. For a few years now, many people do laser pinning, mostly with nanosecond lasers. Here the project is to do comparable work with a femtosecond laser. So the pinning is a technique which consists in putting a laser beam on a material, creating a pressure wave, which creates inhomogeneous plastic deformation in the material. And as a consequence, there are some residual stresses created after this shock. And those residual stresses can enhance the resistance to fatigue failure of the material. The interest of femtosecond laser pinning in comparison with the nanosecond is that it avoids the plasma spreading during the shock. So there is no interaction between the laser beam and the plasma. As a consequence, there is no need for a sacrificial layer on the material. So this could be this could allow some new techniques. And last, it consumes less energy than a nanosecond. So the objectives of this flame project are in three parts. First, to simulate the laser metal interaction, to understand well the parameters of the laser we can change to have some results. Second, we'll characterize the residual stresses and the dislocation density. And last, we'll validate this method by assess the fatigue life of the irradiated specimens. Some works have been done through a master thesis at the Laboratoire Georges Friedel too, on aluminium and titanium. And those results shown that that there is a very different and huge difference between the materials. So we will try to work on various metals in a way to understand well which physical properties of the metals are influencing on the results. So we will work on aluminium, titanium, copper, tungsten, and iron. So we'll first present the simulations we'll do. To simulate the laser metal interaction, we are using molecular dynamics. So it consists in considering the atoms of the material and apply the Newton's equation of motion on each of these atoms in a way to understand the behavior of the material. To do so, we use the software LAMPS, which stands for Large Scale Atomic Molecular Massively Parallel Simulator. And this software uses the Verlet algorithm to integrate Newton's equation of motion, as we said before, and to simulate the laser pulse, we have to put a TTM model, which is a two-temperature model, so which simulates the equilibrium between the electron temperature and the lattice temperature. So as you can see on this scheme, we put the laser pulse on our sample. Then we calculate for a wide region the TTM-MD model, and thanks to those simulation, we have some results. So these are the first results we have. Here we can see the pressure as a function of the time after the pulse of the laser. We can see so the propagation and the attenuation of the pressure through the depths of the material. And from those simulations, we hope to know the best parameters we will use then in experiments. The second part of the work will be to characterize, thanks to X-ray diffraction, the residual stress and the dislocation density in the material. Sorry. First, we can do X-ray diffraction in the laboratory to understand the average behavior in the material, and then we'll do at the synchrotron some measurements to understand the link between the gradient of the pressure in the material and the gradient of the dislocations in the material, which will give us the understanding of the creation of those dislocations. And by understanding the creation of the dislocation, we'll know which is the origin of the residual stress. To do so, we'll use, as I said before, XRD measurements, but also SEM, TEM, and EBSD. And the last part of this work will be to validate this method by assess the fatigue life of the material. To do so, we will produce some microbeams on which we'll do a micromechanical test by putting a down force on those microbeams, and then measure the number of cycles to failure. And we hope through those validation to know exactly which is the effect of the residual stress on the hardening and on the fatigue life of small objects. So the perspectives, as I said mostly before, is to predict the optimal condition for femtosecond laser pinning, to understand the behavior of the various metals and the influence of the physical properties of these metals on the pinning. And last, to understand the impact of the femtosecond laser pinning on the fatigue life of micro components. So thanks for listening. If you have some questions.